Welcome, everyone. Thank you for joining in, and thank you, DARPA, for organizing this workshop. My name is František Brabec, and I'm excited to have this opportunity to present to you the progress our team made since the beginning of the Subterranean challenge, to show you where we are today, and to share where we'd like to get in time for the final challenge. First, let me introduce the team that has been building the solution for the DARPA Subterranean challenge over the last few years. Robotika is an international team based in the Czech Republic, Switzerland, and the United States. There are 5 organizations involved: Robotika International, Robotika.cz, Czech University of Life Sciences Prague, Center for Field Robotics, and the Cogito team. Overall, there are approximately 15 team members. Our core team consists of several seasoned computer science researchers as well as hardware and software engineers, some academic and some with industry backgrounds. Throughout the years, we have also collaborated with various contributors from subject matter experts to undergraduate students. As a non-sponsored team, our philosophy and our goal when building a solution for the Subterranean challenge is to reuse as much of what we and others have already done, and now vice versa. Whenever additional work we perform towards reaching the sub-T goals, let's make it such that it's applicable for other purposes as well. Therefore, our overarching goal is to keep developing a general-purpose self-driving solution which can be used with some tweaks and optimization for the sub-T challenge, but for many other purposes, whether academic or commercial as well. For the same reasons, we are striving to develop this solution using common and affordable components as much as possible. This, in turn, increases the practicality of our solution, where it can be acquired and deployed more readily, with less concern about its cost and risk-benefit analysis that would come to focus for more expensive platforms. Our software is embodied by OSGAR, a portable and customizable self-driving platform, which is implemented in Python and is published as open source. There were only 3 months from official announcement of the rules of Subterranean Challenge to the qualification deadline for STIX in December 2018. We had experience with autonomous robots, mostly thanks to Robotour competition that we are the organizers for, but none for underground environments. We started with platforms we already had and worked to make them fulfill the submission requirements. We used the extreme programming approach for fast iterations, test inadequate environments as much as possible, and kept the system simple in order to be able to modify rapidly. Because of a misunderstanding where we thought there would be a virtual STIX as well, we also worked hard on developing a solution for a simulator and ROS, the robotics operating system. As a result, Robotika was the team that scored the first point back in 2018. It was not necessary as it turned out later, but our goal to add 1 successful artifact report a week helped us to achieve the qualification requirement of 8 artifacts in 2 months. It also freed us to focus on system and test additional ideas in the real world. The feedback from the STIX event was extremely valuable, not just in terms of software and hardware, but it also helped to define the core team around which the larger collaboration would happen. The key lessons learned were the need for the self-protective behavior of robots, to trust time only, everything else, sensor measurements, etc., could be incorrect, and the need for symmetrical robot design. The initial expectation of scoring points at this event was scaled back, and our focus became on making the robots survive and to bring them successfully back to the staging area. The video in the lower right corner is showing robots starting one by one and entering the tunnel environment. The LiDAR scan readings, green points, are turned into a map. The orange line indicates the robot's trajectory. There is no SLAM employed, so you can see how precise or not the estimated position is on return. This video is based on logs collected from the actual competition runs. Throughout the video, you can also see images of other robots which were incorrectly detected as artifacts. For the system tunnel circuit, we doubled the number of robots compared to STIX, worked out the logistics to make them fit into standard airline luggage, traveled by plane from Europe, and ran the first competition circuit. The new machines were fresh, and the progress was visible on a daily basis in Pittsburgh. As the Robotika team members came from different parts of the world, this was also the first time we fielded all our robots together in a mine. One of the most costly lessons we learned at this event was that once an artifact is reported to the operator, there should be a timeout, and if an operator does not react, the system should report the artifact automatically. We lost points when the artifacts were reported to the operator, but he did not forward the findings to DARPA. In retrospect, our biggest weakness was focus on individual robots in isolation and not enough effort on making them work as a team. While we had a strategy, the concurrent launch of all 4 robots was a challenge. Also, the pre-planned options for changing strategy during the run were too limited. Nevertheless, Robotika scored a couple of points. On the virtual side, the virtual tunnel simulator at the time was still rather rudimentary, but with 4 X2 robots we deployed to collect few points, despite the robots sometimes not receiving sensor data, some not even being able to leave the staging area. The 3rd place among non-sponsored teams was a great success and sparked the next wave of motivation for the team. It also helped to cover the expenses for the system track. The urban circuit for us was mainly about integrating the depth cameras for both system and virtual circuits. Also, the newly integrated rear sense tracking cameras helped with robot localization. Half of the robotic platforms were new running hybrid ROS-OSGAR system, which was not stress tested. The extra month between the end of the virtual circuit and the start of the system contest was good, but not sufficient. New small platforms, Mobos and Maria, turned out to fit well into the environment with narrow door passages and showed importance of diversity. Robotika scored in each run but lost points on artifact detection task, which was still only semi-automatic. Due to the COVID-19 situation, our hardware development was put on hold. As a result, our software team could focus fully on virtual, but we all missed the connection with the real world. Working with real-world robots that break easily forces you into a more robust development process. In the virtual world, you can relax more, as you can always restart when things go wrong. We integrated new virtual platforms, started using fleet of drones, introduced full 3D exploration, and upgraded artifact recognition with deep neural networks. We also visited a couple of caves to get a better understanding of the challenges the environment might pose. It was great that DARPA broadcast a showcase of all 16 competing teams. We could see that different strategies led to victory of different worlds, and the Robotika was in the first place twice. Also, our virtual Freya robot explored 4 kilometers, which was the longest distance of all robots among all runs. As the drones followed the ground, they explored only the lower parts down to minus 170 meters in one of the winning worlds. Overall, Robotika scored on the 3rd place among non-sponsored teams. So where are we today? What would we have used in a cave system circuit if one took place? Our robot suite is more varied than ever. We have a tricycle, skid steering 4 and 6-wheel articulated robots, tracked robots, and drones. In our sensor suite, we utilize 2D LiDARs, depth and tracking cameras, IP cameras, stereo cameras, depth detectors, IMUs, odometry, and a gas detector. Our suite of algorithms include wall following, trajectory following, corridor navigation, and local obstacle avoidance. From the humble beginnings of isolated robots, we now have multi-vehicle collaboration strategies. And finally, our base station supports the human operator better than ever. After numerous system and virtual runs, what can still be improved? Everything. From this perspective, we don't mind sharing our code base as open source, as we know that in order to rank more competitively, more major changes and improvements are needed. In the virtual world, the new marsupial platforms looked promising, but nobody actually used them among the 16 competing teams. We have already finished a couple of runs with Explorer R2 and see some advantages. Drones can do fast exploration, but due to the limited battery time, they can only be used for the 1/3 of the total available runtime, even less if the finalists increase the runtime to 90 minutes. Our strategy might change such that the ground vehicles travel as far as they can, and then drones launch and go beyond. The recent development was focused mostly on rapid exploration with a small set of robots, which facilitates faster cycle on Cloud Sim, but for the finals, we might strive to maximize the exploration time and use the whole time window. This will probably require tighter team collaboration and organizing meetings at remote places at given times from which the collected information will be aggregated and delivered to the base. For the system track, we would like to have automated robot deployment as we do in the virtual world. We would also like to make artifact reporting fully automatic without the need of operator intervention. Finally, we might have two-step artifact validation where in the last moment, we might extract most promising hints from collected data among the whole team and report those as artifacts. While it would be nice to have a plug-and-play system where you can easily swap in and out parts of the robots, in reality things are more difficult. One solution was demonstrated at the urban circuit where our seemingly diverse platforms shared subsets of components, modules consisting of combination of hardware and software. NVIDIA Jetson running ROS with tracking and depth real-sense cameras attached provide map data to the robot. As is often the case with hardware, driver compatibility can be a challenge, so this dedicated Jetson RealSense smart node was one universal solution. Another unified element for all robots was a long-range radio and OSGAR sub-T core software. As a result of this modularity, the self-driving suite to a branch new mechanical chassis can be done in a few hours. In one anecdote, a newly built clawback K3 robot moved for the first time, and only an hour later the self-driving suite was applied and the robot was ready to take on the sub-T exploration task. A student remarked that it was wonderful how robots are born smart already. On the downside, a unified platform means that a single problem can bring the whole robotic fleet down. For example, if all robots have the same sensor integrated the same way, and this sensor fails in a specific scenario, then potentially all robots will fail there the same way. From this perspective, Freya, which remains separate and runs a different system, acts as a backup. However, it does not benefit from the tight team integration. Perhaps having two sub-teams would be a good balance between these pros and cons. One of the observations made back at Styx in Colorado was that a robot can end up in situations where the only way out is to back out along the original trajectory. This problem can be solved on the hardware side, make the robotic platform symmetric. This upgrade was applied to all our new designs and are represented by Freya and Clawback K3 pictured here. The symmetric design also facilitates what we call the zigzag recovery strategy, which we first successfully utilized with Clawback K2 in Pittsburgh. We ran into scenarios where the sensor suite was not observing any obstacles, but the inertial measurements were suggesting that the robot was not moving. This implied that the robot is stuck behind an obstacle it cannot see. The solution was to virtually flip front and back, increase the safety buffer around the observable obstacles, return a few meters, and repeat. Once the area where the problem was encountered was passed safely, the changes in the buffer parameter are reset to original values, and the robot continues its exploration. The wall following is a favorite algorithm used in the micromouse competitions, meaning 2D environments with well-defined walls. In 3D, it is much more complicated because a wall can be a negative obstacle, i.e. a hole, or a blocked passage seen from afar can actually be a steep ramp going up. The terrain traversability was getting progressively more difficult with each circuit. In the tunnel circuit, there were almost no obstacles in the path that the robot needed to take. In the urban circuit, steep ramps, stairs, rails, and railroad ties started to appear. In a cave circuit, anything can happen, and if you are too cautious, you don't get to cover much in your exploration. There were several versions of the wall following algorithm. The first maintained the exact distance to the wall, not taking into account anything except the nearest obstacle. Later, an optimized version was developed which analyzed LiDAR scans for gaps. This worked well in small urban rooms, which could be explored without need for the robot to enter such room. On the flip side, a typical example of a wall following optimization failure is an apparent dead end seen from 10 meters, which you might need to move further towards so that you can confirm this observation. There can be a ramp up at the far end. The key parameter in this algorithm is the distance to the wall that the robot should maintain. The value of this parameter evolved over time and currently represents the minimum passage width into which the robot should still go. In the virtual tunnel circuit, we apply two different values based on the role of the given robot, either Save or Pioneer/Deep Explorer. It is possible to prove in 2D that if you enter a static maze following, say, the left wall, you will return on the right side of the entrance. This is not true in 3D, as some parts can be interpreted via sensors as either wall or a passable direction based on the robot's 3D orientation. Imagine a robot driving into the room on a steep ramp down, which is later classified as a wall. Then the robot would drive around this room forever. Drones can also be used to follow wall strategy, but the danger is getting stuck in loop is much higher. Imagine large stones creating steps at the height where the drone wants to fly. Then any slight change of the height generates a completely different 2D slice. The only solution is to be able to detect the loop and to recover from it. The cave strategy attempted to switch the wall side during exploration, but in practice it turned out to be more complicated than, for example, in a tunnel circuit. The prerequisite for the strategy to be successful was that it was moving through a corridor narrow enough so that the robot can see and change the swap of walls seamlessly. If that corridor ended with an obstacle, such as a large stone column, then the robot quickly closed the loop. After experimenting with it for a while, we abandoned this switch-in feature. Since our joining the Subterranean challenge, our plan was to develop a solution that could be applicable to both system and virtual robots. The problem to be solved in virtual and system worlds are not fully compatible, as the system rules allow for a human operator. We underestimated the benefit available from leveraging the human operator in a tunnel circuit. Subsequently, Robotika introduced Control Center, which gives the operator more control and capabilities. In the virtual cave, DARPA introduced the concept of a team base, so the system and the virtual tracks are much closer to being equivalent problems now. Our software development is typically initiated in the virtual world, and only later we move to validate it on the real robots in a real-world environment. The testing in real world usually uncovers some special cases not seen previously in the virtual world. Of course, real-world testing also evaluates the hardware components and the overall robot design, so plenty of real-world experience is needed as well. We really like the feature where the real-world environments and real-world robots were converted into models available in the virtual world. Even though, again, the virtual experience is not 100% identical, it goes a long way towards facilitating seamless transition between the two worlds. One note about the system to virtual transition: the computational power is much more limited on the real robots, so often additional optimization is needed to make the real robots perform well using the algorithms developed in the virtual environment. Then these algorithms are later propagated back into the virtual world. As I mentioned earlier, our goal always was to keep developing our solution so that it remains applicable for the widest range of self-driving scenarios possible. This approach allows us to offer our products and our skills commercially as well. One project we are currently working on involves a collaboration with Ferret, a manufacturer of, among other things, trains for mining environments. Currently, their trains require a human driver, even though some of the tasks are rather mundane. A mining train might be going 1 mile on tracks back and forth all day long, a great potential application for automation. While the train sits on tracks and steering is not an issue, the environment it operates in can be quite dynamic. Rockfalls, other vehicles, even people can potentially enter its path. Further, these mines can be found in very inhospitable parts of the world where extreme heat or cold are common. Fog, rain, dust, smoke can be a common occurrence as well. All these conditions put strain on a self-driving module, as causing a real damage or an injury is a possibility if something doesn't go according to the plan. Just some observation at the end: the number of robots and the complexity is increased with every circuit. It is a coincidence that Robotika had the same number of deployed machines in virtual and system circuits so far, but the number is increasing, and for the finals we plan to have even more robots, 1 person per robot. Also note that with the increased number of robots, the correspondingly increased amount of work required from the human operator becomes unsustainable. So our motivation for developing fully autonomous mission control is really high. At some point, deep in the caves or tunnels or any other space, the robots will have to decide on their own, so why not practice that already today? Finally, we are grateful to DARPA for sponsoring this amazing event. We are glad we can hopefully contribute at least a little bit to the advances in this area. As the awards we have collected so far are really appreciated and keep us pushing on and coming back. Thank you.